emission. And a very famous example of that is shown on the fourth slide, where I've added the Planck all-sky image that shows how remarkable it is that we can learn so much about the magnetic field across the galaxy and all the star-forming clouds that exist in our galaxy. The angular resolution of these measurements is only about 1/10 of a degree, this imposes some limitations. For nearby clouds, the maps are beautiful for 2 or 3 of the closest clouds, but in many cases, we really need better resolution to study the important physical problems that we're addressing. And slide 5 introduces the TOLTEC polarimeter, and I want to point out that it has a lot of pixels, which I'll come back to. It's very important that we have so many pixels, and it has excellent resolution, two orders of magnitude approximately better than Planck. I'm going to talk about both of these, but we can now move to slide 6. And this is an outline of what I want to talk about today. So the first 3 parts of my talk will be focusing on the magnetic field strength, and in particular, how it varies with spatial scale. And I'm talking about the field strength in comparison with gravity and turbulence, other important ingredients. I'm going to show how we can try to measure this, and then in the last part of the talk, I'll give some updates on the technical aspects of how the progress in developing this new capability at el Gran Telescópio Milimétrico. Okay, on slide 7, I'm starting now with this idea of magnetic field strength relative to other components, and I've only got one slide, pretty much only one slide that's fully devoted to the theory. And this is from a collaborator of mine, Cheng, and it discusses some theoretical expectations of how the magnetic field how we expect that it will depend on spatial scale. And if you look at the equations in the bottom left, I don't want to focus on them too much. They're very schematic, but it makes the point that the magnetic field energy density is only dependent on the field strength, but the energy density associated with turbulence is expected to scale, has been known since Kogomorov in 1941. It is expected to scale in some approximate way with linear scale, in that the turbulent velocities decrease as you go to smaller and smaller scales. So these first 2 equations indicate that turbulence will dominate at the largest scales if the magnetic field strength is constant, which from Zeeman measurements, it's believed to be constant over some range of large scales due to collapse along field lines. Now, moving to gravity on the smallest scales, here the scaling is very different, of course. You can tell from the equations, and gravity becomes more and more important at small scales. And so you see a picture, the plot in the upper right of this image shows that as we go to bigger spatial scales, we start with gravity being dominant at the smallest. And then based on the equations, there's certainly the possibility that magnetic field could be dominant at some intermediate scales, but that we do expect turbulence to be dominant on the largest scales. And this is very schematic, of course, but I think it's a good thing to keep in mind as we as we begin to think about the observations. So I talked about the different techniques that are used to measure magnetic field strength. And as we advance to the 8th slide, number 8, you can see this is a slide I've taken there from a review paper in Protostars and Planets. What it's showing is the estimated magnetic field strength using the DCF technique, Davis-Chandrasekhar-Fermi technique, which basically looks at the degree of disorder in the magnetic field. A highly ordered field is almost certainly strong compared to the gas motions, a very disordered magnetic field is likely dominated by the gas motions. And there's a lot of uncertainty in these results from the Davis-Chandrasekhar Fermi technique. But it is used to measure whether a property called the Alfvén Mach number, which tells you whether the magnetic field is dominant or subdominant. I do want to point out something important, which is on the previous slide, spatial scale was increasing to the right. On this slide, the smallest spatial scales are on the right and the largest are on the left. So it's inverted. The horizontal axis is inverted. But the general impression one gets from this slide is not that different from the previous slide. And now I'm going to put my own impression on top of this. If you look at slide 9, then you see a fat red line that I've drawn just to indicate where my eye tells me the Alfvén Mach number tends to go. And you do see that, in fact, at the extremes, at the largest on the left and the smallest on the right scales, the magnetic field seems to be subdominant, as expected from theoretical considerations. Now, the rise on the right is due to gravity. That's a little clearer. So I'm going to focus on that because that's much more relevant for TOLTEC. Okay, so on slide number 10, this is a very schematic way of showing what are the range of spatial scales over which we expect the magnetic field to be important, and in particular, what is the small spatial scale at which we expect gravity to be completely dominant. And we can calculate this in a very crude, approximate way by converting the number density at which the gravity begins to dominate from the previous slide, very approximate, looking at my red line and where it begins to rise and cross over to where the magnetic field becomes subdominant. If we convert that to a spatial scale, we get approximately 2,500 AU. And so we can take this as a rough idea of when we expect magnetic fields to be dominated by gravity. And again, it's very crude, but it gives us some guidance, I think. And this slide shows that focuses on the small scales at which the magnetic field becomes no longer dynamically important. I want to introduce some terminology here. In the previous slide, I talked about the Alfvén Mach number, and I said if it's greater than 1, then you're in the case where the magnetic field is subdominant. If it's less than 1, then the magnetic field is dominant. I'm going to introduce some new terms. We talk about super Alfvénic turbulence as the case where the turbulence dominates the magnetic field, and sub-Alfvénic turbulence as the case where the magnetic field is dominant, and the turbulence cannot dominate the magnetic field, or the gas motions, whether they be from turbulence or gravity, cannot dominate the magnetic field. So it's a little backwards from what you expect from the magnetic field's perspective, but those are the terms that are used. So on slide 11, I'm showing a rough idea of how some of the best instruments used for mapping magnetic fields, and also including what we hope will become one of them is TOLTEC very soon, and it shows the range of scales that they can sample. So in Alma's case, the size of the primary determines the largest spatial scale that's accessible. And in the case of Pole 2 at the James Clerk Maxwell Telescope, or TOLTEC, sorry, just checking. I'd like you to just check that my connection is still good. Can you still hear me?
Yes, we can hear you.
Thank you so much. I don't have access to the chat because I'm looking at my presentation, so I just wanted to make sure. Thanks, very kind of you to check, to confirm. So again, as I was saying, in the case of Pole 2 at the JCMT, a very productive instrument, and TOLTEC, what you're limited by is the angular resolution of the telescope. And for this particular slide, what I've done is I'm focusing on Gould belt objects because they're some of the most nearby star formation examples. Their distances range from about 100 to about 400 parsecs. So for sort of a geometric mean of 200 parsecs, these are the scales you get. So this is very schematic, but it does illustrate how ALMA and POL2 don't really fully capture the range over which magnetic field is supposed to be dynamically important. TOLTEC seems to go a bit beyond, cover a lot of that range and go a bit beyond, so we can maybe approach, look at the slightly more distant Gould belt objects. Okay, the other thing, last point I want to make with this slide is that if you really want a seamless coverage of spatial scales, so you can watch how the magnetic field changes as you go across deep into a cloud, from the cloud to the core to the info envelope. To do that continuously, it's attractive to consider the possibility of feathering. It's a term that's used when you combine ALMA data with single dish data. It's called feathering, and it does require a lot of overlap in spatial scales, and TOLTEC will be really ideal for that technique of feathering. Okay, the last slide I have before I move on to part 2 is slide 12, and here I just show a kind of a picture of some of the facilities that are used commonly for mapping magnetic fields. And I really want to focus now on the pixel count, how many pixels an instrument has, because these objects are extended, and the more pixels we have, the quicker we can map an object and move on to the next object and map a lot more sky. So on the upper left of this image, you see Planck. I talked about Planck. On the bottom right, you see ALMA. I briefly mentioned ALMA, which is doing a lot of great work on mapping magnetic fields. So that covers the extremes of the scales. And for the intermediate scales, the pictures I'm showing here are of facilities I will be mentioning in this talk. Although I won't mention Hawk plus Sophia, but Enrique Lopez Rodriguez will be speaking later, and we'll talk a lot about that. So you'll be hearing about that one as well. Okay, so I'm now ready to move on to the second part of my talk, which starts on slide 13, and I'm now moving to a different method that's used to assess the importance of magnetic fields, which does not rely on the disorder, but relies instead on the relationship between magnetic field direction and elongation of structures. And this is a technique that's come on strong recently, and it was motivated by the kinds of Planck measurements that you see in this slide from a paper in 2016 from Planck, which shows this relationship using something called the alignment parameter. So the alignment parameter ranges from +1 when the magnetic field runs parallel to a filament, for instance, or -1 when the magnetic field is perpendicular to elongated structures you observe in column density. And 0 would be sort of a case where there's no clear pattern. And Planck began very detailed statistical analyses of this that showed that as you go to higher column densities, the tendency for magnetic fields to be parallel to filaments begins to disappear. And this motivated the work that you'll see on slide 14, which was to introduce this powerful technique to measure alignment parameter called the histogram of relative orientations, or HRO. And this paper came out also in 2016, a little bit later. And this is work that's been led by Juan Soler, who's at Rome now. And what Juan did was to pick out the 10 clearest cases of dense molecular clouds that he could resolve with Planck, and try to extend the analysis to the highest possible column densities. And he does see evidence that, in fact, the alignment parameter switches from parallel to perpendicular. Not in every one of the 10 clouds, You can see there's some cases where it's, 2 cases where it's still, even at the highest column densities that Planck can probe, it's still close to 0. But overall, there's a clear tendency, I believe, for the discovery of an important transition, which I call the alignment transition from parallel to perpendicular alignment. And this, there's been a lot of follow-up work. I don't have time to go into all the citations, but a lot of follow-up work discussing this transition, what it means, and how it compares to a similar transition that's seen in the magnetic field scaling from the Zeeman data. But I'm not going to talk about this right now because I want to focus in particular on the key result of this 2016 paper, which is shown in slide 15, which is a comparison of simulations and observations, where in the bottom plot you see the simulations done for 3 cases: strong, intermediate, and weak magnetic field. The weak is the blue, and that's called the superalfanic. Weak magnetic field is the superalfanic case. And what the Planck team noticed, led by Juan Soler, was that the weak field simulation, the superalfanic simulation, did not cross around 10 to the 22. It maybe at very high column densities it might cross, but it doesn't show a clear transition at all in the simulations, whereas the observations shown at the top do show a clear or at least evidence for a transition. So based on this very influential paper, it was concluded that in fact in agreement with the Davis-Chandrasekhar Fermi results that I showed you, there is a range in which the magnetic field is dominant over the gas motion. And now we should be able to continue to look at higher angular resolution than Planck was able to achieve in order to see whether we can see the evidence for loss of influence of the magnetic field. Planck does not have the resolution to see that, but there's a lot of groups trying to look at HRO analyses of higher resolution data. Slide 16 shows an example from work by Chad Hull and collaborators. And what you see here is an HRO analysis with the theory on the bottom. I'm just showing the images, not the actual HRO plots, and the actual ALMA data at the top. And this is now doing HRO analysis on much smaller scales. And Chad Hull reached the conclusion that it's exactly the opposite situation. The Planck team was able to rule out the superalfanic case. And Chad Hull in this image, although he only had one target, so you have to be careful to check with other targets, but Chad Hull was able to rule out the subalfanic case. So it seems that maybe the HRO technique is showing us the same loss of influence of magnetic field at these smallest scales that we saw with the Davis-Chandrasekhar Fermi method. But we certainly need a lot more work, and this is an area where TOLTEC could also be able to play an important role. I do want to mention that we have to be careful in interpreting this HRO evidence, because the transalfanic case was not ruled out by Planck nor by Chad Hull. So a lot more work is needed to be sure that we actually do have a transition from subalfanic to superalfanic that can be observed with the HRO technique. Okay, so I'm moving now to slide 17, which is the beginning of the third part of my talk, where I'm going to talk about a very new idea, or I should say maybe not a new idea, but a frontier area, very difficult kind of experiment to do, and that's to look and see whether we can trace the magnetic field continuously from across a wide range of spatial scales. This, of course, is important for assessing the importance of the magnetic field. If it can maintain its orientation as the collapse is continuing, almost certainly it can be playing a role in the collapse. So this continuity is, I think, is going to give us very important clues for the role of magnetic fields in star formation. So I'm just going to show a couple of examples because this is a very new area and there's not a lot of concrete results yet. But slide 17 shows, I think, a very nice case of a low mass core very nearby where the data from the POL2 instrument, which I've talked about already in this talk, shows a similar magnetic field direction as the large scale field measured by Planck. Now, so this has been published very recently, okay? And I want to now move to slide 18, which shows another example. This one is even newer. It's actually unpublished. This is by my own group. Paul Williams, my student, is now graduated and is a postdoc at the Lawrence Berkeley National Labs. But what Paul was able to do is to study magnetic field continuity in the Vela C cloud, which is the cloud that I started this talk showing you about. And he was able to use some very nice ALMA data that was obtained by Laura Fissel. So what Paul was able to do, before I tell you what he was able to do in a paper that I hope will be submitted this year, I want to show you the target that we looked at. So this target is called BLAST J090028, and it's a very massive core. Now this is a much further object than the one I showed you in the previous slide. It's in Vela C at 900 parsecs away, where we know the large-scale magnetic field very well. And what Paul did was to look at this target. And this first picture just shows you a little bit about what kind of target it is. It's a massive dense core, but it seems to be a young one. It's IR quiet. This map shows you the molecules in green from this structure. And structures this massive don't just form one star, they form many. And we can see the beginnings of star formation in this object with the PAX emission at 70 microns in blue, and this new ALMA polarimetry data. Here, I'm just showing the IMAP in red. That's also showing some of these structures. And the source that has red and blue right in the middle, it's got red. It's the brightest red dot, which also has blue around it. That's the target that we observed that's the target where we got actual polarization data. And this next slide shows the polarization data. So slide 19 shows the actual polarization data. And you see at the upper left, you see a small part of this map I showed you at the very beginning of the talk, which shows the Vela C South Ridge region and the blast vectors in white. On the top right image, you see a zoom in on our core, the one that I told you about, blast J090028. And you see in yellow there this core. Now you're looking at the dust emission from the Polka instrument, and in pink you see polarization vectors from the Polka instrument. And then on the bottom right is the black vectors. You also see the pink vectors in the bottom right from Polka, but you see the black vectors from this ALMA data. What's interesting is that the magnetic field direction seems to be preserved across all these scales. The bottom left plot shows these polar histograms. The blast vector at the center of this core is within 5 degrees of the average value of all the ALMA. So this is yet a second example of where it appears the magnetic field is able to maintain its continuity. We think maybe it's because it's such a young source. Certainly when high mass star formation sources evolve, the magnetic field gets shredded and highly distorted. So Now, I really want to caution you that there are other examples where we can't find this continuity, and so this is very much early days. But this is, I think, an important area of research where TOLTEC can really make a very important contribution due to unique ability to probe scales that are difficult. You see how difficult it is for POLCA to really study this core clearly. It has only a few hundred pixels, and TOLTEC should be able to do better on these kinds of objects. It won't be able to see this particular source because this is very, very far south, but sources like it. Okay, so on slide 20 now, I'm moving to the last part of my talk, which is on the progress of getting the polarimeter operational and the instrument operational. So this project it's called TOLTEC. It's been a long time that we've been at it. We first got our funding in 2016, and there were a lot of delays from COVID. But we have been at the Gran Telescópio Milimétrico for almost a year now, and it's been a struggle to get down to 0.1 Kelvin. But we're there now, and I'll show you the camera's working very well. Of course, you probably know the size of the telescope is what gives us so much power for this kind of work, and of course the site is an excellent site for working at 1 millimeter. A few details about the TOLTEC instrument are shown in the bottom right panel here. I've talked a lot about the 5 arcsecond resolution that we get. We get that at 1.1 millimeters. We also have other channels at longer wavelengths as well, all observed simultaneously. I'm going to go into the schedule in a lot more detail in the next few slides, but just an overview is that we did get our first light, which I'll show you the images of that over this past summer. The commissioning is ongoing. A short break in August when the weather was not good, but there's a lot. The team from UMass was here last week. My team from Northwestern is here this week, and the call for proposals, as many of you know, has been issued, and we're hoping to start on our 4 public legacy surveys and on observations from the community in January of 2023. So this slide 21 shows that what makes it possible to get all these pixels is a new technology for detectors called kinetic inductance devices, and these are pictures of the arrays before they were installed. The team at UMass is shown at the upper right with all the filters and beam splitters that allow the detectors to observe simultaneously inside the cryostat. They operate, as I mentioned earlier, at 0.1 Kelvin. So it's a real challenge. A lot of help from Arizona State University and University of Cardiff built many of the components, and University of Michigan, many other universities involved in this cryostat. The slide 22 shows the contribution of my own group at Northwestern. So we are, in order to make polarization measurements in the presence of the 1/F noise that we have from the detectors as well as the atmosphere, we will be spinning a half-wave plate in front of TOLTEC. And you can see a few pictures of the half-wave plate rotator in this slide. Ever since it was completed several years ago, it's been tested in my lab at Northwestern in the upper left, in 2019 at the University of Massachusetts to make sure there was no interference with the detectors. And then in the lower left, you see Dennis Lee, a student in my group who's doing his PhD on this project, and Emir Moreno, who's the chief of the day crew, testing in late 2021. Testing the half-wave plate rotator at the LMT site. The rotator, there were some challenges. It's all warm, the half-wave plate rotator, but there were some technical challenges in developing it. It has the half-wave plate and the structures that hold it and allow it to spin weigh about 20 kilograms, and we're spinning it at 2 revolutions per second, and we have to minimize the vibrations, which would cause detector noise. And we also have to measure the position to about 5 arc seconds accuracy because of the because of the synchronous offsets, half-wave plate synchronous offsets that all systems, all rapid spinning, continuous rotating half-wave plates have. Those have to be measured carefully and removed. That's why we need that accuracy. We chose to use an air bearing for this purpose. We also use an integral torque motor and a commercial high precision encoder. So you'll notice in these pictures there's no half-wave plate. Slide 23 shows the status of that. As of last month, the fabrication of our half-wave plate in Cardiff University was finally finished, and the testing was completed last month. And they tell me it's the best half-wave plate they've ever built. But they still need to mount it to its mount and ship it to us. So it'll be another week or 2 before we are able to come back here and install it. We're down here now doing we're installing the half-wave plate rotator onto the front of TOLTEC. That's one thing we have not done yet. All the testing, all the commissioning work I'm going to show you was done without the half-wave plate rotator installed. But hopefully that will happen this week. Okay. The last slide I have on the instrument is slide 24, and this shows on the bottom left the excitement when I was there about 10 months ago, and the camera was lifted up to the receiver room. That's the photo on the bottom left with the crane. On the upper left, you see the TOLTEC in the receiver cabin with all the associated refrigeration, electronics, and signal electronics. On the upper right, you see our first light image. So this is a quasar BLAC, and this image was taken before we finished focusing. And we were very happy to see that we do get the 5 arc second resolution that we expect from a 50-meter telescope. So I think I'm down now to just one more slide. So that's slide 25, where I'll get to tell you a little bit about the plans we have for one of the 4 legacy surveys that TOLTEC will do. Actually, there's more than 4. There's 10 planned, but only 4 selected. And the one I'm going to tell you about is called the Fields and Filaments Survey. And what we're doing here is we picked 5 nearby filaments to look at, and a couple of more distant IRDCs. They're listed in the bottom right. The 5 filaments are all Gould belt objects. And in the slide on the left, I show another legacy survey, a plan for another legacy survey called C2C, Clouds to Cores, which will map much larger sky areas with the 5 arc second resolution, of course, and will be trying to characterize large numbers of cores. And what we'll be doing is zooming in and doing deep integrations on small portions of the C2C fields. Like here you see in Aquila South, we're looking at one particular filament called Serpent South that we're zooming in on. This is one of the 5 nearby clouds we're looking at, and the zoom in shows what we'll be observing. We expect to get about 70,000 independent measurements of magnetic field direction over all these filaments that we'll be looking at, and hopefully we'll be starting this the actual survey in January. Okay, so on slide 26, I summarize some of the results I wanted to tell you about. So the first bullet I have here talks about the idea of constraining the magnetic field strength, and in particular, the need to do that on scales that are very difficult right now to access cleanly. And these are the scales extending from the cloud scales down as far as 1,000 AU, and how we can use different techniques like Dave's trying to check the Fermi histogram of relative orientation to try to understand how the magnetic field affects star formation process at the smallest scales, that where it can still control things. Then I talked a little bit about this idea, which is it's a very much of a frontier area of trying to trace continuity across scales. And I showed you an example from Vila C, another example from Ophiuchus, from Kate Paddle's work. And I think I want to emphasize, I think this is an area where TOLTEC can really shine, especially if we can use the feathering technique in conjunction with ALMA. And then finally, I tried to show you a little bit about the current status, and that we're hoping that we're on the threshold of being able to make these measurements. So thank you very much. I'm happy to take any questions. Hello? Ah. See a hand raised, but
Hi, this is Dave. Hi, Giles. Can you hear me?
Aquí sí te escuchamos, pero no sé.
Nosotros tenemos una...
Está muy fuerte ese, ¿no?
Hello. Hi, Giles. Can you hear me?
Vamos
Ok.
a intentar con esto.
Pregúntenle ya mientras.
Ya.
Porque de verdad están preguntando. Bueno. Can you hear me?
Yeah.
Giles, can you hear me?
Tiene el micrófono apagado. Yo creo que alguien activó los micrófonos. Apagó.
Hola, ¿me pueden oír?
Sí.
Nosotros sí te escuchamos. No sé
sí.
si tú nos escuchas. ¿Sí nos escuchas?
Giles, ¿me escuchas?
Sí, yo escucho ahora. Yo no sé qué pasó, pero mi conexión de teléfono se apagó, pero ahora todavía tengo la computadora y puedo oírles con la computadora. Y parece más o menos bien esta conexión.
Sí, está
quiero
muy bien.
preguntar
Te
si
escucho muy bien.
ustedes podrían oír hasta el final de mi presentación.
No hubo problema. Ya tenemos una pregunta de Marcial.
Sí.
Hi, Giles, can you hear me?
Yes.
Great. Yes, I have a question about the scales of the HRO method. I saw that you showed some graphs were extracted from Planck measurements, observations, but
Yes.
this method applies for smaller scales. Do you have, or have you seen any observations with ALMA, for example, or is this a trend of the HRO method observed on small scales?
Yes, if you go to slide number 16, can I ask someone to advance to slide 16 so I can answer this question? You can tell me when you've reached slide 16.
Yes,
I see it. Okay. I have some delay, sorry. Yeah, so this should answer your question. I covered this very briefly because I was moving quickly onto continuity, but this is a paper by Chad Hull that shows an observation of a star-forming region in Serpens that Chad Hull, you can see the vectors in the upper right, and Chad Hull was able to use some AREPO simulations shown from Harvard, the bottom right, from MOX. And the HRO, I don't have the actual HRO analysis on this slide, but they did do an HRO analysis for both the observations on the upper right and for the simulations on the lower right. And what they find when they do the comparison is that the magnetic field does not appear to be dominant. It is either, we either have a super alphanic or a trans-alphanic situation. So the magnetic field must be comparable to or weaker than the gas motions. And the gas motions are presumably driven by gravity, almost certainly driven by gravity on these scales. So there is this one case, but there are other cases. My own student, Dennis Lee, wrote a paper showing that the transition from parallel to perpendicular is in Ophiuchus does continue when you look at Hawk data, and it's a very active area of research. Probably one of the key results is from Thushara Pillai's Nature paper. I don't have the reference handy, but it's a cloud in Serpens where she used Hawk data, and she was able to see a slightly different I guess the best way to see it is that she was able to find that in some filaments that are not near the center of the cloud, but are more outlying filaments, she was able to see a transition back from perpendicular to parallel. But this is a very subtle thing because you don't see it in the main filament. You only see it in what she calls secondary filaments, these are not the diffuse filaments that Planck looks at, but they're filaments that appear to be feeding the main filament, and or laterally feeding the main filament. So I would urge you to take a look at her Nature paper if you haven't, because it does extend this technique to smaller scales. But this is still relatively recent. This technique was only invented, unlike the DCF technique, which was invented in the 1950s. This technique was only invented proposed in 2013 and first used in 2016. Does that answer your question? Okay, I couldn't tell if I answered your question, but hopefully you can still hear me.
We can hear you on Zoom.
Great. Did I answer the question successfully?
I think so, but okay. Anyways, I'm going to go ahead with my question here. Very nice talk. So I have two questions, and I just want you to comment on them. The first one is you showed a really nice plot where Kate Patel actually compared the alpha and Mach number with number density, and we see that there's a dip slightly where the number densities are around 1,000 to 10,000. So could you comment on the reason why B field becomes important in those densities? And then the second question is One thing particularly that we have to consider when we are comparing B field across various spatial scales and trying to see how the B field is preserved from clouds to cores is that we are just only looking at the plane of sky directions and we're not considering the different components. So when we talk about how B field is preserved in all these different scales, we miss out the components in all the other directions. And I think that should be taken into consideration in future in the community. Yeah, so those are
So let me
two things. Yeah, I just want
great. Let me start with the second question because I think that's the easier one to answer. I think that you're absolutely right. The two results I showed you, and I hope I made this clear, could be just due to accident. It could be that it's very rare for a magnetic field to be strong enough to preserve its direction from cloud to core. But at least the example from my own group, we suggested that maybe it's possible when the core is very young. We happen to by good luck find a very young core. It's a infrared quiet. Massive dense core with very low brightness at 10 microns. So apparently in a very early stage. But it's certainly true that this alignment could be coincidental. And in fact, it may not exist when you look at the full three-dimensional field. And this is why we really need a lot more data. The only way we can be sure that this continuity is real is if we can see in many targets and we can do a statistical analysis that takes into account the full three-dimensional structure of the field.
right. Yeah.
Now, yeah. So coming to your first question, the reason I think that the magnetic field can come to dominate and on certain scales is the following, and this is also discussed in the textbook by Bruce Drain. A very nice presentation there, and it also appears on my slide.
You're losing you, guys.
See here. Hello?
Yeah, okay. Now
Oh,
it's okay. Yeah, we lost you for a minute.
I see my. Okay, I'm actually thinking I'm going to try to call in again if that's okay. While I'm talking, I'm going to try to call in on the phone because I do believe the phone connection was stronger. So I'm just going to, while I'm talking, I'm going to do that. It should not take me very long. Okay, 1 second. Okay, I just have to enter the 915. Okay, give me another few seconds. Okay, I'm going to mute myself.
Can you hear me now?
Yes, we can hear you.
Great. I think this is better. I think at some point someone I got an incoming call that somehow interrupted me at the very end of my talk. I think that happened. So I'm back. I can see the slides, but I'm back on I think a more reliable audio connection. I apologize for the interruption. So I wanted to ask if you could go to slide number 7.
Yeah.
Okay, so in slide yeah, oh, we're not there yet. Well, at least I can't see it yet, but I'm assuming you'll get there soon. Oh, there it is. Okay. So slide 7 shows, I think, answers the question of why magnetic fields should ever be expected to dominate. And in particular, I'm going to start on the largest scales, which in the plot on the upper right is shown, is on the right side of the plot where you see the blue line called turbulence dominates. So we believe that on the very largest scales, the turbulent motions dominate over the magnetic field. For example, supernova explosion, things like that. But one of the characteristics of turbulence is that as you go to smaller scales, the turbulent velocities are smaller on the smaller scales. This is Kolmogorov showed L to the 1/3 dependence. Che-Yu argues that in molecular clouds it's a little different. But so if the magnetic field strength is constant as you go from scales a little bigger than molecular clouds to molecular cloud scales, submolecular cloud scales down to a few parsecs, as you move in that direction, you do expect there to come a point where b squared over 8 pi is bigger than the kinetic energy associated with a small scale turbulent gas motion. Yeah. And so that is why it's possible the magnetic field may come to play an important role in the dynamics. But then gravity eventually, as we know, will dominate. So the question is there this intermediate range where magnetic effects can be important? I think many theorists think there is, but we definitely need more measurements. I showed you some measurements that support a subalfanic magnetic field, but we need more.
Yeah, that's even though this is a really simple plot, it's pretty good. Yeah, thank you.
Okay.
Thank you for the good question.
Thank you, guys. And we will thank again our speaker.